So we're going to finish up the exponential and logarithmic chapter by talking about word problems, and specifically they're going to be called exponential growth and decay and modeling problems. So let's start out by just talking about continuous growth. So what we want to say is this is a different kind of growth than like what we talked about when we were saying like money in a bank where it was like compounded quarterly or something. This kind of growth is something that's growing every second of every minute of every day of every year, right? So it's always growing, it's always changing. So that's called continuous. This is often related to things like population, and it doesn't matter if we're talking about a city or a state or a country, and I'm going to talk about a lot of those today. It could also be an amount of bacteria or a virus, or just think of things that are alive, right? So those kind of things are growing all the time. So this growth can be modeled by this function, a equals a naught e to the kt. Let's break down what that means. So this a naught, like a with a little zero underneath it, is an initial amount. So it's where we started. So when we're looking at things growing, we go, okay, from some particular population size, then we're looking at it getting bigger. So that the a naught is where do we start. K is the rate of growth. It could also be decay. It depends on what the substance is doing, if it's getting bigger or smaller. So if it's positive, it'll grow. If it's negative, it'll decay, and we'll talk about that more. T is the amount of time. Time could be in years. It might also be in hours or seconds or minutes. So you kind of have to watch how the problem is phrased so you can pick up on what's going to happen. And I have a couple of different things that we'll look at today. There's a second equation that's pretty identical to that. It's a equals pe to the rt. I find that students like it because they can call it PERT. It sounds like a word. People like to be able to say a word where I don't really know what you would call that ae to the kt kind of thing. It doesn't sound like a word. So what's the same? A is both the future amount. This p is the principal or the present value. It says here's where we started. So p is just like a naught. E is still e. The rate is like the k. So it's how is it growing or getting smaller. And t is still time. So whichever one of the ones you want to use is fine with me. I might switch back and forth as we talk about it as well. You might see one thing more in like a physics class. You might see something different in a math class, but I want you to think they're the same equation. So just really quick to point out the difference between growth and decay. It all comes out to the rate. So that k or the r. When it is positive, so if k is greater than 0, the function is growing. Might be going really slow, doesn't matter, it's growing. If it's negative, the function will be decaying. So sometimes you have to know to put the positive or the negative number in with it. So a word problem may tell you something's decaying at a rate of 5%, then you need to remember to put in negative 0.05 when you go to put it in the equation. So pay attention that you may have to put a sign with something. And then the last little thing on this page says if the rate of growth is expressed as a percent, like I just said 5%, you need to make sure you change it into a decimal before you put it into any kind of equation. So equations will always have decimals when we use percentages. All right, so let's start small and then we'll just continue to grow it as we go. So let's say that the population, and let's not just say, I actually look things up, right? So the population in Europe was 736 million in 2010. And at that time, it was growing at a rate of 0.2% per year. So we could take that population and turn it into this function that p of t is 736 e to the 0.002 t, where p of t is going to be in millions and t is going to be the number of years after 2010. So notice that 0.2 as a percent, I need to move 2 decimal places over when I go to put it as a decimal into the equation. And again, I just want you to see like what the wording is doing. So all this wording was just an explanation of what the function is. So the real question says, use the function to find the population in 2000. So very first thing we need to do is express t, right? So t is going to be our time. So make sure you look at the wording. T is the number of years after 2010. So if I'm at 2020 minus 2010 says we're looking at what happens in 10 years. So we're going to evaluate P of 10. So this means you're going to grab your calculator and you're going to put in 736 times 0.002 times 10. And my pen does that weird thing, so sorry about that. I suggest you try that now, even if you need to pause the video to do it, because I want to make sure you know how to use the calculator, and it's important that you take the time to see if you're getting the same answer that I'm going to get. I'm going to go ahead and give this to 1 decimal place. Know that homework, assignments, whatever will tell you how many decimal places that you're supposed to put. So I get 750.868, so to 1 decimal place that would be 0.9. Remember, this is in millions. If you're not getting this number, you may need to put parentheses around this. Like if you put it in and you hit E, it should have maybe an up arrow if yours doesn't go up to the exponent, and then you would want parentheses around the 0.002 and the 10 to make sure you're getting the 750.9 million. So an easy first example just to introduce the word problems. So I'm going to stay with this. I'm going to stay with this idea of this is how Europe was growing and say, well, can we figure out when the population will reach 775 million? Right. Look at it, says give the answer as a year. So here in the future, I want it to be 775 million, and that's 736 e to the 0.002 t. So I'm solving for time. I discuss a lot that when you're solving exponential equations, you'll often find yourself needing to divide, then take the natural log, then divide again. So step 1 here, because there's no plus or minus or anything else happening, I want to try to get this e by itself. So I'm going to divide by 736. Okay. When I do that, I'm not going to put it in my calculator. I'm not going to turn it into a decimal. I'm just going to leave it alone. And I'm going to say, okay, now the 775 over 736 is e to the 0.002 t. I did leave a little space in front because after I divide, the next step is to take the natural log. So I'm going through my steps, divide, log, divide. So on the left side, nothing happens. I have the natural log of 775 over 736. But on the right side, the natural log of e to the 0.002t is 0.002t. So that was the purpose of introducing the ln, was to have it be the inverse of the e, which brings the exponent down. And now I can do my last step, which says, oh, I should divide again. So I have 0.002, 0.002. Now is the time we grab our calculator. In your calculator, you should have parentheses around the 775 divided by 736. So I have the natural log 775 divided by 736. Close the parenthesis and then divide by 0.002. Okay, so this says 25.8, right? If I do 1 decimal place. Notice it asks for the answer as a year. So since the answer is going to be a year, I'm going to go ahead and round this up to 26 because this says 26 years later that our population will be actually over 775 million, but we're just going to do traditional rounding now. Remember, t is the years after 2010, so my final answer is I have 2010 and I add 26, which says this is in the year 2036. So that's when I should expect 775 million, and a little bit more actually because we rounded. Okay. So similarly, I'm going to stick with the idea of looking at population. And again, I looked this up, that in 2008, the population of Colorado was 4.93 million. In 2018, it was 5.69 million. So we're just going to assume that the growth was continuous and figure out what the rate of growth for the state was. So we want to go through and kind of like pull everything apart and say, like, what do we have? What if I treated this one like PE to the RT? Okay. So P would be, what did I start with? Which I started with 4.93 million. And in the future, we had 5.69, so that was A. So where did I start? Where did I end up? I'm looking for the rate, so I don't know what that is. But the time, I can see that was 2008 to 2018. So I'm going to subtract. And I get 10 again. 10 was just, I picked nice numbers for us to have. All right, so I'm going to write this down. I'm going to say, okay, 5.69 is equal to 4.93 e to the r that I don't know times 10. Right. Remember that little thing I said last time? Divide, log, divide. So these are the steps I want to do. So step 1, divide. And I'm going to divide by 4.93. our goal is always just to get the e by itself. And just like last time, I'm not going to do anything with that 5.69 over 4.93. I am going to give myself a little space. So here, and I am going to say this is 10r so that I can put the natural log in. Okay. The natural log of e to the 10r is just going to be 10r. So now I can divide by 10. So I have the natural log of 5.69. Oops. I kind of want that to be bigger. There we go. Over 4.93. So that whole thing, that whole fraction, I'm taking the log of. And then I'm going to divide that by 10, and that's going to give me the rate of growth. So once again, I grab my calculator, and I say the natural log of 5.69 divided by 4.93. Now I close the parenthesis, I divide by 10, and it tells me the rate of growth. And let's do 4 decimal places this time. I have 0.0143. Okay, so this is what the question was asking me. So it's a 1.43% rate of growth for the state, and that's how it went from 4.3 up to 5.69. Okay, so we're going to change a little bit, and we're going to talk about Halflife. Halflife, hopefully, like logically makes sense what it is. It's how much time needs to elapse for us to have half as much in the future, right? So I know I'm going to say this wrong because I have no idea what the substance is. I just looked up some Halflife stuff and picked one that had a pretty number. So this is the half-life of, I'm going to say Cymborgium, it's probably wrong, is 30 seconds. And that's why I picked it, because it was 30 seconds. 30 seconds is a very nice number, so I thought let's use that. So this says if I start with 0.16 milligrams, find the number of milligrams at the indicated times. So what happens is every 30 seconds, I'll have half as much as I had before. So I'm starting with 0.16 and 30 seconds passes. So now I have half as much. So I have 0.08 milligrams. Okay. So notice 1 minute is 30 more seconds has passed. So I have 0.08 over 2, which is 0.04 milligrams. So I'm hoping you're starting to get the idea of half. Is I have half as much. So 90 seconds, which isn't 30 more seconds has passed, over 2, you get 0.02 milligrams. And then the last one, I divide by 2, and it's 0.01. So as long as the period of time between each of our calculations is the half-life, I can just divide by 2. So half-life is that, just half. That's all I want to know is half as much. There are some shortcuts that are going to be super helpful when we look at Halflife and also for doubling time. So I put them together on the same slide just so that you have them all at once. If I want to figure out the time or how much time it takes for there to be the half-life, if I know the rate, I can do that natural log of a half divided by r, and that'll tell me how long the half-life of a substance is. So I have this little equation that I think is really worth writing down. The other equation that I put with it, just so I could put it all on the same screen, is how long it takes something to double. So the half-life is when things are decaying, and doubling time is when things are growing. So if we want to know how long it takes for it to be twice as much, then I use t is equal to the natural log of 2 over r. Maybe somewhere you've seen this before as the natural log of 2 over the absolute value of r. That's also true. This requires you to think about, is r positive or negative and all that kind of stuff. And I thought, why bother? So I gave 2 formulas when traditionally most textbooks you would see you would give 1. But I think it makes so much sense that half-life would have natural log of a half and doubling time would have natural log of 2, that having one more equation, totally worth it. Totally worth writing 2 down, because I think it will help you, because it just relates better and you don't have to worry about the sign this way. All right, so let's start with this. The population of Las Vegas is growing at a rate of 3.67%. So if it continues to go this way, how long will it take for the population to double? So our formula was, this one is doubling time because it's a growth. So it's the natural log of 2 over r. All right. So my time, how long it's going to take to double, will be the natural log of 2. And remember, we always express percentages as decimals. So there we go. And sorry that try to erase this little thing, but then I'll have to put the 3 back in. Sometimes it just makes a stray mark. There we go. All right, so I'm grabbing my calculator. I'm putting in the natural log of 2, close the parentheses, divide by 0.0367, and it says 18 point, was like 88. I'm just going to write 89. This is in years, and what I would say is the assumption is, unless I say otherwise, time is in years. It's generally how the formula is given. When I want it to be something else, I will tell you what it is. Like, remember that one we just did like 2 slides ago that said seconds? So I knew it was in seconds, but if it doesn't say it, then I'm assume it's in years. So this says in 18.89 years, whatever the population of Las Vegas is now, I will have twice as many people, right? That's important for cities to think about when they're planning for streets, when they're planning for schools, when they're planning for how many restaurants and hospitals and everything else they have, is where are we now? Where are we going to be in the future? Also important would be to look at bacteria. So another application of this doubling time. So here I said a bacteria in a petri dish is growing at a rate of 7.25% per hour. Now notice I changed the time. So I want to know how long will it take for the bacteria to double. So this answer that I get for the time is going to be in hours, but still it's the natural log of 2 over r. So my r is 0.0725. So I grab my calculator, natural log of 2, I divide by 0.0725, and it says this is 9 point, I'm just going to do 2 decimal places, this is hours. So in about 9.5 hours, I will have twice as much bacteria as what I started with. Okay, so let's flip it and let's go back to Halflife. So this one, I decided we would use a couple of things that we all see every day. So let's start with plastic bottles. This says the decay, or the rate of decay of a plastic bottle is 0.0015. And this is years again because I didn't say anything else. So I want to find the half-life of a plastic bottle. So now I want to use a half with the natural log, and then, oops, because I said a half, I wrote 2, but divided by r. So let's just write an r to start. Okay. So for this particular example, I have the natural log of a half. Now the r, it's a rate of decay, so I need to put in negative 0.0015. So I told you sometimes you're going to have to relate that together and look that I didn't give you the negative with the rate, but we need to pull it in. If you didn't do it, you would get answer that time is negative, and time can't be negative, and that should clue you in that something should have happened. So I'm putting in my calculator the natural log of a half, and then I'm dividing by negative 0.0015. And it says time, and I'm just going to say round it to the nearest year. This is 462 years. I wrote it too quickly. Okay, so it says it takes about 462 years for a bottle to be half of what it was, right? So like to decompose that much. So it's not completely gone. I just have half as much waste as I used to have. So let's think of something else that we also think of when we think of plastic bottles. We probably think of plastic bags. So I'm telling you this time that the half-life of a plastic bag is approximately 20 years. I found things that said it was between 10 and 20, so I went, let's just say 20. So I want to find the rate of decay of the plastic bag. So I'm asking a different question this time. We have this formula. T is the natural log of 1/2 over r, but this time I told you T, and I want to find r. Right. Traditionally, when we have a fraction and we want to get rid of the fraction so I can solve for anything, I can just multiply both sides by the denominator. So now I'm going to have 20r is equal to the natural log of a half. And then I'm just going to come back and divide by 20. So I have r is the natural log of a half over 20. So here, ln of a half divided by 20. This says negative point, let's do 4 decimal places, 0, 3, 4. And then the next one, I have a 6, 5. So the 6, 5 says, let's just go round that up to 7. Important that you put the negative with it so that we can see it's a decay rate. I expect it to be negative as the answer. It came on its own negative out of the calculator. All right, so we're going to try to put this together with a bigger problem now. So I have the half-life of silicon-32 is 710 years. The 32 is just the name for the type of silicon. So there's different types of silicon, so you don't use it, it's just a name. What we do care about is the 710 years. It says if 30 grams are present now, how much will be present in 300 years? We'll check that out in a minute. I can't do anything until I figure out what R is. Right, so that's my goal. So I'm back to that. T is equal to the natural log of 1/2 over R. It says half-life, so I use the one that has a half in it. And just like the last one, I gave you T and we're looking for R. So I have 710 is the natural log of 1/2 over R. Just like last time too, I'm going to multiply the R on both sides. So I end up with 710R. And let's see if we can make that look a little better. Is equal to the natural log of 1/2. So I divide by 710. So R is the natural log of 1/2 over 710. So here's step 1. So I put in my calculator, natural log of 0.5 divided by 710. All right. So I want to show you what my calculator did. So let me go ahead and put what I got, but then I want to show you just in case your calculator does it too. And I'm going to flip over to the calculator so you can see it. So here is my calculator, and I'm going to put in my natural log of 1/2, and then I'm going to divide by 710. Okay. So what I wanted you to see that this comes up with scientific notation. I got a negative 9.76 e to the negative 4. So the scientific notation says the fourth number on the right of the decimal place should be a 9. And then the 7, 6, whatever will follow after it. So I wanted you to see this notation and how it happens. We can go back here to the regular screen and I'll write it out for you as well. So if you want to see that my calculator said negative 9.76 e to the negative 4 means I put a decimal and then I count 1, 2, 3, and then the fourth one is that 9 and I put zeros in front of it because I verbally said to you, let's go ahead and make it the 5th decimal place. So that 7, 6, I said, let's make it an 8. All right. So that's what I have now. Let me see if I gave myself room. I didn't. Okay. I'm going to somehow make it fit all in here. So here's my rate. You can kind of see it. So I'm going to erase that part that I just put on so I give myself some more room. Now that I have that, I can go back and start to answer the question. So the original question was if I have 300 or 30 grams now, how much will be present in 300 years? So I'm looking for A, how much will I have in the future? If I start with 30 grams and then I have E, the rate is negative 0.00098 and then times my time is 300. So this is, just put this in your calculator, see what you get. 30 e to the negative 0.00098 times 300. And I do want you to be practicing this to make sure you know what you're doing. Let's do 2 decimal places. So let's say I get 0.36. So I have 22.36 grams. I want you to see the gravity of this. 30 grams, right, was 300 years ago. But because this half-life is so long, after that much time, you really haven't lost much, right? So the bigger the half-life, the more of the substance is going to stay around in the long run. So let's get bigger on that. Bigger on that is something that we talk about a lot anytime we talk about exponential growth and decay, and you would see this probably in a biology class as well, or physics or chemistry or something, is like carbon-14. So carbon-14 they use often to figure out how old something is. The reason they use it is because it has a really long half-life. So you can see here what I underlined. It says a fossilized leaf contains 15% of its normal amount of carbon. And then we're going to use 500 or 5,600 as the half-life of carbon-14. So that's a really long half-life. We just had one that was 710. Now we have one so much bigger at 5,600 years. First question I have is, what is the decay rate? Right. So the decay rate, remember we talked about T, is the natural log of a half over R. We've done this is our third time. So 5,600 is the natural log of a half over R. I think we've done it enough to see that the R is going to come up, the 5,600 is going to come down, and we're going to put that in our calculator. So I'm putting in the natural log of a half, and then I'm going to divide by 5,600. Again, I got some scientific notation. I got negative 1.2 and then e to the negative 4. So my rate is negative 0.000. That 4 says here's my 1 and there's a 2, so I gave you 5 decimal places again. But my calculator said negative 1.2377, whatever, e to the negative 4. So that 4 says this is my fourth number. All right, now we're going to figure out how old the fossil is. To figure out how old the fossil is, I'm going to use A equals A naught e to the kt. And this R is really the K, the same thing. Oops, I kind of got carried away writing. Get rid of that. That's not supposed to be there. Okay, so what's happening? First of all, what's happening is I don't have any idea what A naught is, so let's leave it alone. I know K is that rate I just solved. I'm trying to solve for time. So the only other piece of information I have is this 15%. Of whatever amount it started with, there's only 15% left now. How do we know that? Well, we know how much carbon-14 should be in a leaf that was alive, so we can go to one that's dead and just do a comparison, and it says there's 15%. Okay, so we took a lot of steps to get here, but I want you to know this is my same steps: divide, log, divide. So step 1, divide. What am I dividing by? I'm dividing by A naught. So it's going to cancel on the left, and luckily it will also cancel on the right. That's how we're able to solve this question, is that the A naught disappears. So now I have this nice little 0.15 equals e to the negative 0.00012t. This, then I throw in the natural log, which we know is going to make the natural log e part go away, and I'm going to end up with 0.15, oops, natural log of 0.15 is negative 0.00012t. At this point, to solve for t, we've divided, we took the natural log, we're just going to divide one more time. So I can say that the natural log of 0.15 over negative 0.00012, this will be my t. Again, grab the calculator. So I have the ln of 0.15. Make sure you close the parenthesis. And then divide by negative 0.00012. Okay. I'm just going to round it to a year. I have 15809. So this says it's 15,809 years old. That's why I didn't put the 0.33, because really nobody cares if it's 0.33, right? There's some amount that this is an estimate. We'd probably be happy with just you saying there are 15,800 years, right? Like if you were reading an article in a journal or something, like the 9 years doesn't add a lot of value to it. And if you were doing that, you would talk about accuracy and precision and, you know, significant figures. We don't care about that. We just want to be able to do this, these calculations where I'm using the half-life, putting it together with continuous growth and decay, and figuring out how old it was. All right, we're going to take a little switch, and this is our last type of problem, which is a logistic growth model, and I'm going to show you this on my calculator as well. I think it'll help. So this says the logistic growth function f of t is 53,000 over 1 plus 1,324 e to the negative 1.2t, models the number of people who have became ill with a particular infection t weeks after its initial outbreak in a particular community. A says how many people became ill with the infection when the epidemic began. So I'm asking you, initially is 0. Okay, so anytime it began, that's like initial, so we put in 0. So this is 53,000 over 1 plus 1324 e to the negative 1.2 times 0. So you could put this whole thing in your calculator, or if you want, you can do this little shortcut. The negative 1.2 times 0 is 0. So this exponent is 0, so I don't have to put them in. E to the 0 is 1. So actually, I don't have to put any of this in. What I can put in my calculator is something much smaller, which of course I always like that if I don't have to put as much stuff into my calculator. I only need to put in the numerator, I'll switch back to my pen, 53,000 over 1 plus 1324, which is really 53,000 over 1325. So that's what I'm going to do in my calculator, is put in 53,000 divided by 1325, and it says 40. Okay, so this says this infection started with 40 people. 40 people were sick, and maybe it's just 40 people were sick before people realized it was an epidemic, right? Like if 1 or 2 people are sick, nothing's going on. If all of a sudden 40 people are sick, maybe we start looking at it, okay? That's the thought. Part B says, when will 14,500 people be ill? So this is my amount in the future, and this is the equation that we started with. So my goal is to solve for the time. I'm going to clear the fraction by multiplying both sides by that denominator. Okay. So on the right side, it just goes away. On the left side, I have this 1 plus 1324 e to the negative 1.2 t times 14,500. So let's distribute. I'm going to multiply 1 times 14,500, which gives me 14,500. And then I'm going to multiply the 14,500 times 1324. Okay, so the 1324 gives me 19198,000. So there's a bunch of numbers. It's okay. I still have the e to the negative 1.2 t, and this is equal to 53,000. Distributing is probably the easiest way. There's other ways to do it, but I feel like this is the easiest way, and I always want to show you the easiest thing to do. All right. So next step is I'm trying to get to the e. So I need to get rid of this 14,500. I don't need it. I mean, I need it, but I need it to go away. I don't want to unaccount for it. So I still have this 19198,000 e to the negative 1.2 t. But then I have the 53,000 minus 14,500, and that gives me 38,500. From here, this looks like divide, log, divide. So step 1 is divide. Okay. So that leaves me on the left with e to the negative 1.2 t. On the right, I have 38,500 over the 19198,000. Just to make my life a little easier, I'm going to get rid of 2 zeros on the top, 2 zeros on the bottom, just to have a little bit less numbers. So now I have 385 over 19198,000. So that's a little bit better. I'm going to take the natural log of the left. I'm going to take the natural log of the right. On the left, I'll end up with negative 1.2 t. On the right, I have the natural log of 385 over 19198,000. Almost to the last step. I divide by negative 1.2, I divide by negative 1.2, and then I grab my calculator. Okay, so I put in natural log 385 divided by 19198,000, close the parenthesis, then divide by negative 1.2. It says 5.17. I'll put the 176, let's call it 5.18. Right, again, I'll tell you in the problem and it'll say in the homework how many decimal places, but for now I'll just do this. This stands for weeks, because if you go back to the beginning, it says weeks. So in 5.18 weeks, it will go from 40 people that started up to 14,000 people that are sick later. They should all sound scarily familiar to you, like in our everyday lives right now. All right, one more question it's going to ask, which is not what's going to happen to us, but I have to ask it anyway. How many people become ill overall? This is not what's happening. Okay, so just know I'm going to tell you this thing, but then I'm immediately going to say that's not what's happening with our society right now. So this says if we did nothing to intervene and we just let things go crazy, as t gets bigger and bigger, well, what's happening is e to the negative. E generally looks like this, like it's increasing, but if it's e to the negative x, it's decreasing. And where is it going towards? It's going to 0. So in the long run, this e goes to 0. So I end up with 53,000 over 1 plus 1324 times 0. So in the long run, this goes away, it becomes 0. Well, 1,324 times 0 is 0. So I end up with 53,000 over 1, which is 53,000. Really what this is you'll also see problems that say limiting size, like what's the limiting size? Maybe that would make you feel better about this problem, is if there are 53,000 people in a city, that's the most that can get sick, right? If we're, like if we have a closed population, then we could have less people get sick, but we couldn't have more than 53,000. Sometimes in math we call it a limit, just to say, like, is there some kind of bound, like, 1 million people can't get sick if there's only 53,000 people in a particular city. So that's what that question was asking. I did 2 more of those on another video that I posted. I'm going to quickly just go back over to the calculator. I just like to show you, I did put this in the calculator, so this is that function that I just had, 53,000, 1 plus 1324 e to the negative 1.2. I had to call it x because it doesn't have t. And I gave it a window. Oh, I guess my window got messed up because I must have done something else. So let's give it a smaller window. So let's say I just look at this from 0 to 20. And I'm going to do like 0 to, I don't know, I'm going to do 55,000. I would never make you do this, but I want you to see what this looks like just as a curve, because I think it's interesting to see. We would call this like an S curve because it kind of has an S look to it. So what's happening is at the beginning, there is this big growth. Like you can see, it looks exponential to a point. And then at some point, it starts to slow down. So at first, it's increasing really, really quickly. And then over time, it decreases more slowly. If you're a business major, you are going to hear about things like this in the future. We call these things like a point of diminishing return. Like, where did it change from increase at an increasing rate to increasing at a decreasing rate? So there are important things to talk about this in economics. So it can apply to medicine, it could apply to business. So it is an important thing that you will see again. I won't make you graph this. It's way too complicated to graph. If we graph it, we use a graphing utensil, which means I would graph it for you, or you would have a picture. All right, so that's the end of today, but make sure if you need to see those other problems that I did post them in the announcements.